Today, lesson 6, we're looking at what happens in the nucleus. Okay, so we've already spoken about two forces, a strong nuclear force and an electromagnetic force. So the electromagnetic force is due to the protons plus charges, they repel, and the strong nuclear force is the opposite force, or the force that holds the nucleus together. Now, the electromagnetic force is what we call an infinite range, okay, in that it gets smaller and smaller and smaller further apart the plus charges are, but it's still technically there. The strong nuclear force is very different in that it has a very short range, about the size of a nucleus, okay, even smaller than some nuclei, and once you go outside that range, it disappears, it cuts off. So it's a huge force within the range that it operates, and then zero force outside of that. Okay, so it's quite an unusual force. You saw in the video clip that you've looked at again there, and that you saw on Saturday, Jim Al-Khalili explaining to you in terms of Velcro. Very nice explanation it was. Okay, so basically, let's have a look, right? Okay, this is a nucleus, or this is an area where a nucleus can be. Okay, I'm putting in a small nucleus in here. Okay, right? This area is effectively the area that the strong nuclear force operates. Outside this area, it doesn't operate at all. Okay, right. So in this scenario, okay, there is an electromagnetic force of repulsion, okay, and there's a strong nuclear force of attraction. It's a small nucleus, okay. The electromagnetic force of repulsion is in a good position because there aren't that many protons and neutrons, and the strong force is between protons and neutrons. So if there's not that many of them, okay, it isn't as effective. So effectively, when a nucleus is small, okay, the strong nuclear force isn't as effective as it could be, right? If we increase the size of the nucleus and get it to this spot, okay, so if we have a nucleus, pardon the shocking drawing, okay, if we have a nucleus where it is around the size, the exact size, which is about 10 to the minus 15 of a meter, where the strong nuclear force operates, okay? So there are lots of protons and neutrons. The strong nuclear force is fully operational, so the strong force is very strong. Okay, the electromagnetic force is still there, but the strong force is winning. This is iron. This is the iron nucleus. This is the perfect scenario, the most stable, iron. And this is the magic point, okay? This is where we all elements want to be, right? Iron nucleus, okay? Right? Once it gets bigger than that, we have another problem, okay? Once you get bigger, okay, right, you'd expect a strong force to be getting bigger and bigger because you have loads of protons and neutrons, but the problem is that it's going outside the range the strong nuclear force operates. So once it gets bigger, it becomes less stable again, okay? So iron is the magic one, it becomes less stable, right? So you've seen a few diagrams or a few graphs. I'm just going to draw one here, just very roughly, okay? And we want to have a quick look at it, okay? Right? So basically, this gives you a good idea. So this is the size as it gets bigger. As the nuclei gets bigger, going that way, right? And then we're interested in basically stability. So this is a very rough diagram now, stability, okay? Now what happens is, right, you get something looking something like that, very similar to that, okay? So as the nuclei get bigger, they get more and more and more stable until they get to this point. And this point is iron, okay? So iron is at the peak. Once you go beyond iron, stability starts getting smaller and smaller and smaller because the nucleus is getting too big, okay, and the strong nuclear force isn't having the same effect. Interestingly, there is actually a little blip here, okay, early days, okay, where there's a nucleus that is actually much more stable than you'd expect it to be, and that's the helium nucleus, the alpha particle, and that's why radioactive decay happens with alpha particles. We'll get back to it, but just be aware of this little glitch here. Helium nucleus is another special nucleus, okay, but iron is the magic one. So what happens? Okay, so regarding fission and fusion, what happens? If the nucleus is too large, it is inclined to split. Okay, it's inclined to split into a smaller nucleus. Okay, more like iron. Excuse me. Okay, more like iron. So fission occurs, and fission is the splitting of a large nucleus into two or more smaller nuclei with emission of energy. We'll get back to energy tomorrow. E is equal to mc squared time tomorrow. Happy days, right? Okay. If the nucleus is too small, it would like to join together with other nuclei to get bigger, and that's called nuclear fusion. Now again, there's a release of energy tomorrow. E is equal to mc squared. Hold tight, right? So basically that's what fission and fusion is. So let's recap. In nuclear energy, we have in a nuclear fission and nuclear fusion reactions, okay, in both cases the nuclei are trying to become more iron-like. In fission, large nuclei are splitting to form smaller nuclei. In fusion, small nuclei are joining, fusing to give large nuclei. Okay. In both cases, energy is released, which we look at tomorrow. Okay. That energy is the E, and E is equal to mc squared. And what is actually happening is some of the mass of the particles is converting into energy, or is becoming energy. But that's tomorrow's class. Right. So, are we happy with that? The next clip, video clip, will kind of repeat what I've done here and probably explain it better. So you'll have a good idea at the end of that. Thanks a minute. Bye bye.